quick look through LinkedIn, and very important to say that he did his first degree at the Ernst Ziegler Gymnasium Kornwestheim, from which he graduated in 2001. Then there is a bit of a gap. We know that he went to Cornell for his PhD in physics, so quite a long stint in the US that continued then with a postdoc at the University of California, Berkeley, and the Lawrence Berkeley National Lab. So he stayed there until 2014 and then decided to come back to Europe and got a university research fellowship in 2014 to come to the UK. Then he got a lectureship in 2016 and climbed through the ranks and became a professor in 2023. So that's really an amazing trajectory and great success here. That is really a testament to Johannes's research, and we'll hear a lot about it. And I had a little poll around collaborators also outside of Imperial, outside of us biased people who are all in your favor, and they say, oh, great, Johannes, amazing, so engaged, always on time, great science, great contributor. So you've really had an impact on all of the research fields and collaborations in research, but also you also contributed a lot beyond the research and also in the department. So Johannes has got a few titles here as director of the MSc, which is a really important role in the department, so thank you for taking that on. And also very engaged in the Thomas Young Centre, so really looking after theory across London, where Johannes took care of events, and then which is one of the hard parts of the job, and then now has become director. So congratulations on that and for everything that you do for the community there too. So we look forward to hearing about the amazing research that Johannes is doing. It's wide-ranging, going from the very, very small atoms. I remember we discussed STM images and imaging molecules. Recently, Johannes also took another plunge to give a LCN seminar like we usually allocate to our new joiners in the department, just because I'm not just doing 2D materials, I'm also doing other things with excitons and chargers, and so very keen to share your research and the breadth of your research, so thank you for that. I think we look forward to finding out more about this part of your research that's related to Moiré materials, and the magical is quite intriguing here, so I look forward to watching you don your top hat and your magic wand, and to hear about all of your work. So thank you very much. Congratulations, Johannes, and we look forward to hearing from you. Thank you.
Thank you very much, Sandrine. It's a very kind introduction. And thank you all for being here with me on this happy occasion. Delighted that my family can be here. Delighted that lots of former and current members of my research group can be here. Some friends, some collaborators, colleagues, students from the department. It really means a lot. Thank you. So today I'll tell you a little bit about the interesting things that can happen when you start putting things on top of other things. So let's start with a brick, right? If you take a brick and you start putting bricks on top of other bricks, pretty soon you end up with something like a wall. The wall can be pretty useful, but you don't have to stop there. You can keep putting bricks on top of other bricks. And at some point, you might end up with something as iconic as London's St. Pancras Hotel. So this act of putting things on top of other things is both very powerful and it's also a very creative act. Now, in my research, I don't work so much with bricks, but the things I put on top of each other are ultra-thin materials such as graphene. So graphene is a two-dimensional crystal that is entirely composed of carbon atoms, which are arranged in little hexagons, and these hexagons form a lattice which looks like the honeycomb lattice that the bees are making. Now, if you take two of these graphene sheets, well, you can put them on top of one another, like this. There's different ways of putting them on top of one another. This is one way, where the carbon atoms of the top layer sit directly above the carbon atoms of the lower layer. This is what we call the AA stack bilayer. But it turns out that bilayer is very rare in nature, and the reason is that the carbon atoms do not very much like to sit on top of one another. But there's another way to put the two graphene sheets on top of one another, which is this one. This is the so-called AB stack bilayer, which has a much lower energy. And in this bilayer, you can see that the carbon atoms of the top layer sit in the middle of the hexagons created by the carbon atoms in the lower layer, and the other way around. So this is a very low energy stacking. But there are yet other ways that we can put two graphene sheets on top of one another. For example, what we can do is we can first rotate one of the graphene sheets and then put them on top of one another. And when we do that, something quite different happens. So what we get are sort of regions where we have the AA stacking, where the carbon atoms sit directly on top of one another, and these regions of B stacking here, like this one, for example, or like this one, right? And so if we look at this so this is what we call a twisted bilayer. So if we look at this at a bigger scale, we see that actually these regions of different stacking arrangements make up a very regular pattern, which is called a Moiré pattern. In particular, when we focus on the regions of AB stacking in this Moiré pattern, what is quite interesting is that they also start to form a hexagon, much like the hexagon created by the carbon atoms in graphene, but with the important difference that this hexagon formed by the AB regions is a much larger hexagon than that formed by the carbon atoms in graphene. So Moiré patterns are actually not only formed by 2D materials. They have been known for a very long time. The word actually originates from a type of fabric, also known as watered silk, that is manufactured by pressing two different layers of material on top of one another, and then you get this sort of watery appearance here worn by Tsar Peter the Great. So it was something rather fancy at the time. I have here a bit of Moiré material. This one is not silk, is polyester, but yeah, you can see it. It has a very nice, maybe this side's better, has a very nice effect. So you can kind of maybe hand this around. So Moiré patterns quite generally come about when you have two very similar patterns and you superimpose them. And one example, for example, is here when you take two fences on two sides of a bridge, and these two fences also create a Moiré pattern. So that's just a very everyday life example. Recently, I was given a lovely book. It's called Moiré Motion by Takahiro Kurashima, and what you have here, switch over. What you have here is sort of a set of lines, and then have another sheet with another set of lines, and when I superimpose these two set of patterns, again, I get a new pattern, a Moiré pattern, and what is interesting, when I start rotating the one sheet of patterns, you can see how that Moiré pattern changes quite a lot. And it's similar with the twisted bilayer graphene. So if you change the rotation angle between the two graphene sheets, you can end up with very different Moiré patterns. So if you rotate the one graphene sheet by a lot, you end up with a sort of relatively small Moiré pattern. But if you make the rotation angle small, the Moiré pattern gets much bigger. Now, this is all quite nice to look at, but sort of as a material scientist, what I'm really interested in is the question, what is the effect of the Moiré pattern on the properties of the material? So let's think about the properties of graphene and of twisted bilayer graphene and see how they're different. So graphene, for example, is known to be a good conductor, actually, similar to copper. In contrast, twisted bilayer graphene, in particular, if you have a rotation angle of close to 1.1 degree, turns out to not conduct any electricity at all. It is, in fact, an insulator. And what is even more intriguing is if you cool it down to a low temperature, it turns into a superconductor, so a perfect conductor of electricity. This is quite interesting because it is, and this is why, here comes the magic. So this is why this rotation angle of 1.1 degree, this is why it's called the magic angle, because something very special happens at that particular rotation angle. Now, these phenomena are quite reminiscent of another very intensely studied class of materials, the cuprates, which are currently the best known superconducting materials, and you can see there are some examples of that family of materials. They have a rather complicated crystal structure, but they also are insulators at high temperature. When you cool them down, they can become superconductors, but the mechanism why this happens hasn't been understood, even though people have worked on this for decades. So this is the reason why when these discoveries were made in magic angle twisted bilayer graphene, that generated a lot of excitement. And here I'm showing you the number of publications with the title Twisted Bilayer in it. You can see that in 2018, when this discovery was made of magic angle twisted bilayer graphene, there was an explosion of research in this field of Moiré materials. And I was very fortunate because I could be in that field right from the beginning in 2018 and make some contributions to that field. So in today's lecture, I'll tell you a little bit how, how it happened that I was in a place that I could make or could participate in that field in 2018. And then I will give you just two quick examples of types of contributions that my research group has made. So I'll start with my own journey, which begins in the southwest of Germany. I was born in Stuttgart. It's down here. This is where I grew up. This is where I went to school. My interest in science began with my very first physics teacher, Dr. Drehmann, who was a wonderful teacher and told me he might watch the live stream, and if he is, herzliche Grüße nach Kornwestheim. So that led to a decision to study physics at the University of Heidelberg. So here you see Heidelberg, it's like a lovely old university town. Now, when I started physics at the beginning, I wasn't interested in materials at all. I mean, I was interested in things like, the Big Bang or the Higgs boson or stuff like that. And so I decided to do a summer research project in the group of Hans-Jürgen Pirner, who was an expert in quantum chromodynamics. So this is the theory of the force that keeps the nucleus together. Now, when I met up with Professor Pirner, he gave me the following assignment, and that was to write a computer program to calculate the electronic properties of a hydrogen molecule. Now, that wasn't what I was expecting, and he probably kind of saw the disappointment in my face when he proposed this project, and then he uttered a sentence that kind of stuck with me, and that was, "Der Appetit kommt beim Essen." And that means roughly the appetite comes when you eat. And he was right. The appetite did come. I found out about myself that I greatly enjoy messing around with computers and calculating the electronic properties of materials, and it's what I do still. So what does that actually mean, to calculate the electronic property of a material? Well, if we take a sort of microscopic look at a hydrogen molecule, it looks like this. So we have the two protons, and they're surrounded by these electron clouds, which are described by a wave function. Now, the shape and the energy of these wave functions are described by the famous Schrödinger equation, which actually celebrates its 100th birthday this year. And I've written it down for you here. Just go through the various terms. So there are terms that describe the kinetic energy of the electrons. There are terms that describe the attraction between the electrons and the atomic nuclei. And then there is a term that describes the repulsion between the electrons, because the electrons all carry a negative charge, so they repel each other. And it's this very last term which makes solving this equation so very difficult, so that we're still 100 years later, we're still working on that very problem. And so we'll come back to this problem later in today's lecture. Now, having found my sort of area of interest, I went on to do a PhD, and as Sandrine said, I went to the US, to Cornell, which is a university in a small town called Ithaca. It's somewhere here in upstate New York, about a 5-hour drive from New York City. There's a lake, there's some gorges with waterfalls, and lots of woods around it. But I had a very good time there, because I worked with a brilliant supervisor, Professor Tomás Arias. Looking back at sort of my PhD, it's mind-boggling how much time he spent with his PhD students and sort of teaching them really the nitty-gritty details of his craft. So that was a very, very, very powerful experience. The topic of my PhD was the computer simulation of liquids, and I'll just show you what my proudest moment was of my PhD was when I was able to derive a new formula for the correlation function of liquid water that allowed us to calculate the nonlinear dielectric response of liquid water in a strong electric field. After my PhD, I kept moving west and ended up in Berkeley. So here is the view from the Lawrence Berkeley lab onto the San Francisco Bay. You can see the Golden Gate Bridge in the distance. And at Berkeley, I spent 4 years as a civet. Now, if you don't know what a civet is, it's a type of cat. And if you not quite sure if maybe I inhaled too much secondhand marijuana smoke on the streets of Berkeley, civets are what the members of Stephen Lewis' research group refer to themselves. Don't ask me why. So I worked with Professor Stephen Lewis for 4 years, who is sort of one of the all-time great electronic structure theorists, and it was just an amazing experience and a privilege to work with Stephen. And the topic of my postdoctoral work was graphene, and in particular, understanding the behavior of electrons in graphene. So let me now tell you a bit about the history of graphene. Graphene is made from a material called graphite, which is a crystal that consists 100% of carbon atoms. And you can see here, it's not transparent, it sort of reflects the light, it's kind of dark color. You might know there's another kind of crystal that is 100% carbon atoms, and that is diamond. So obviously, these two look very different, so you might be surprised that they actually composed of the same type of atoms. And the reason why they have so different properties is, of course, because the atoms, the carbon atoms, are arranged in a very different way. So for diamond, which of course is very, very expensive, the carbon atoms form a sort of three-dimensional connected network, while for graphite, which I could buy a sort of significant chunk like this for 10 quid off the internet, it has a layered structure. Now, these layers are held together by relatively weak van der Waals forces, and as a consequence of that, it is quite easy to peel off big chunks from the graphite, and this is how a pencil works. So you scratch the pencil over a piece of paper, and you peel off these big chunks of graphite. Now, if you want to make graphene, it's a different story, because graphene is actually so thin that you can't see it with the naked eye. So if you actually want to make graphene from graphite, you have to find a way to make the graphite disappear. And this vanishing act was first performed by two researchers at the universities of Manchester, and it was quite ingenious and very simple because all it requires is a bit of Scotch tape, and really not much more than that. And because it's so simple and ingenious, I will try to perform this vanishing act for you. I really should have brought a hat. That's absolutely right, Sandrine. So what do we need? So we need a source of graphite. So I brought a pencil, right? And so we can deposit a little bit of the graphite onto this piece of paper. And now comes the challenging act, because I need to get off a bit of this Scotch tape. All right, manage that. Well done. All right, so now we need to transfer a bit of the graphite onto our Scotch tape. So that we do it simply by pressing down the Scotch tape down, and as you can see, we have sort of a bit of the graphite on our Scotch tape here. And now comes the process of thinning it out. And the way that is done is simply you sort of press the Scotch tape together and release it, and now you have two thinner bits of graphite, and now you keep repeating that process like this, and it becomes sort of thinner and thinner as you do that. And if you keep doing it for about 10, 20 times, you end up with graphene, which you can only sort of see under the microscope. Right? So this is how the famous Scotch tape method works. And the two gentlemen who came up with this wonderful idea were awarded a Nobel Prize for it. So those are Kostya Novoselov and Andrei Gein. Now, as I said, my interest was actually in the electronic properties of graphene, and these are quite special too. So let me tell you why the electrons in graphene are so special. So if you have an electron in a normal material, typically its energy is related to its momentum, which is the product of the mass times its velocity, in this way. So you have a parabola. So the more momentum you have to square it, and then you get the energy. So that's sort of an electron in a normal material. But in graphene, it looks very different, right? In graphene, instead of a parabola, you get a straight line, and that is quite. And to understand why this is so special, we have to go back to this gentleman, Albert Einstein. You probably all seen this formula: E equals mc squared. Means the energy of a particle is equal to its mass times the speed of light squared. Now this actually is a formula that only applies to particles that aren't moving. So if you want to calculate the energy of a moving particle, you have to use a more general formula. So it's this one, which involves the momentum p. Now when we look at this formula, and we look at the special case of mass equals 0, so a massless particle, we can see that the energy will be proportional to the momentum in that case, which is exactly how the electrons in graphene will behave. So in other words, the electrons in graphene behave as if they didn't have a mass. They behave as massless particles, and that explains why they have such a high electrical conductivity. Now, I told you that already that the electrons in twisted bilayer graphene, though, behave very differently to those in graphene. And that was first analyzed by two theoreticians, Rafi Bistritzer and Al McDonald, in 2011. So they solved the Schrödinger equation for twisted bilayer graphene and made a very powerful prediction. They predicted that the Moiré pattern would slow down the electrons. So here's the result for the velocity of the electrons as function of the twist angle, and you see it goes to 0 at the magic angle of about 1 degree. So they solved the Schrödinger equation, but actually they made a simplifying assumption. As I told you previously, including the effect of the electron repulsion makes it very difficult to solve the Schrödinger equation. And so what they had done, they had basically neglected the repulsion between the electron in their calculation. So it wasn't quite clear what was actually going to happen. So what happens when you include this repulsion between the electrons? As I said, it's very difficult to solve the Schrödinger equation. So instead of sort of going into great mathematical detail, I decided to show you what happens. So I've hired a number of actors who will sort of act out the parts of interacting electrons. So if the electrons could please come to the front. So we've got Matthew, Cheng, Stefano, Simao, Wen-Chuan, and Jordan here, who are the electrons, and they sit nicely on the atoms, which are the mats, which kind of represent the wave function. And now these electrons have some properties, right? So the one property they have some kinetic energy, and that means they can kind of hop from one atom to the other atom. So it's kind of... And by sort of moving around, they sort of transport electricity, and you can see how sort of these moving electrons give some electrical conductivity. Now, we can reduce that kinetic energy by increasing the distance between the atoms. So we can sort of spread the mats a little bit more, and that makes it harder for the electrons to hop around. So they will sort of not hop around so frequently, and that reduces the conductivity. Now, that's the one property of the electrons. The other property is that they also have a repulsive interaction, right? So they're kind of not the friendliest of creatures. They kind of don't like to share. So in particular, if they're on the same atom, they will kind of, try to get rid of one another. And it's a bit of a sort of rough and tumble. This repulsion we can actually make bigger if we reduce the size of the wave function. So if we make the wave function a little bit smaller, yeah, and then the repulsion will become even stronger. So what does this repulsion do? It reduces the conductivity, and when the ratio of the repulsion, which is described by a parameter u, to the kinetic energy T becomes too large, then the electrons will stop moving. So at that point, we are in a state where sort of nobody moves, and it's now an insulator. The material has become an insulator. There's one more property that the electrons have under sort of very rare circumstances. Actually, the electrons can also have an attractive interaction, so they become rather friendly to one another. Actually, it's not really understood exactly when and under what circumstances that happens, but if they become friendly and attracted to one another, then they can form pairs, and these pairs can again move through the material, and this is a new state that we call superconductivity. So anyway, let's please thank our actors. All right, wonderful. So with this knowledge of interacting electrons in the back of our minds, we can now appreciate what happens in twisted bilayer graphene when you make it for real. So this happened in 2018. The first experimental realization of magic angle twisted bilayer graphene was reported by the group of Pablo Urillo Herrero from the Massachusetts Institute of Technology, and he reported his discovery at a conference in Los Angeles in 2018. And what they measured was, indeed, when you make this magic angle twisted bilayer graphene, it does become insulating. And when you cool it down to very low temperatures, it does become superconducting. So this created a lot of excitement in the community. I was actually at that conference, so I got a little bit swept up with the excitement. In the meantime, I had started my own research group at Imperial, and so when I came back to London, I wanted to work on this. There was another lucky coincidence, and that was that a bright student joined my group, Zachary Goodwin, who wanted to work on that topic. He was co-supervised by my partner in crime for many years on everything 2D material, Arash Mustafi, and also Arash's postdoc Fabiano Cossetti was involved in the project. And so what we asked ourselves is, what is actually the value of the repulsion to the kinetic energy in twisted bilayer graphene? Now, it turns out it's rather difficult to calculate this because of this complicated Moiré lattice of the atoms. So instead, with dealing with this very complicated Moiré lattice, our idea was maybe we can deal with the simpler crystal of the AB sites instead. So to calculate the repulsion of this simpler crystal, we had to know what the wave functions were of these AB sites. Now this is a bit of a weird question, but using a technique called Moiré functions, we were able to calculate the wave function of an electron on the AB site. These are these orange colored distributions here. What is very interesting is that an electron on the AB side has a wave function that consists of 3 lobes, and these lobes actually sit on the neighboring AA sites. So the electron is actually never on the AB site. The other important observation was that this wave function is huge. Actually, at the magic angle, it actually extends over thousands of atoms. So having that wave function, we were now able to calculate the ratio of u over t as a function of twist angle. So this is our result here. And when that ratio exceeds a certain critical value, which is about 2, the material becomes an insulator. Our first observation was, the first insight from our calculation was actually, there's not just one magic angle, there's actually a whole window, a whole range of magic angles where you should see insulating behavior. That was our first observation. But then we realized we had actually forgotten something. So what had we forgotten? Well, when you look at a real device that is used in experiments, you have your twisted bilayer graphene, which is what we had been studying. But actually, in a real experimental device, the graphene sits on an insulating substrate, and underneath that substrate is a metal, and that metal is connected to the graphene so that we can measure the flow of electrons through the graphene. And we hadn't included the effect of that metal. So what does that metal do? Well, to understand that, let's see what happens when we put 2 electrons into the graphene. Now, these 2 electrons repel each other, and the strength of the repulsion is mediated by the electric field lines. Now, when these electrons are quite close to one another, these field lines stay quite close to the plane of the bilayer. Now, I already told you that actually we know that the wave function of the twisted bilayer graphene is huge, so these electrons are actually not very close to one another, and as a consequence, the electric field lines can actually stray very far from the plane of the twisted bilayer, so much that potentially they can even go through the metal. When that happens, the metal actually plays a role because the metal has also mobile electrons which can then interact with the electrons in the graphene, and that in turn weakens the repulsion between the 2 electrons in the graphene bilayer. So we redid our calculation, taking now into account the effect of the metal, and then we got this green curve here, and it looks similar, but there are some differences. In particular, one thing that can happen is, let's say you're at this particular twist angle here, and if you don't take the metal into account, you think the material is an insulator. But when you do take the metal into account, it's actually a metal. And that is something quite surprising, so you can transform the material from an insulator into a metal without moving its atom or without changing the wave function or anything like that. So that's quite an interesting prediction, and so I went to a conference in Paris actually and presented our results. And afterwards, basically everybody told me that the metal is never going to be that close to the graphene that you could ever see this effect. All right. So I went to another conference and presented my results, and afterwards this gentleman came up to me, Dmitry Efetov, who told me that he's actually doing experiments where the metal is extremely close to the graphene. So here's one of his measurements, where the distance between the graphene to the metal is only 12.5 nanometers. But this looks kind of similar to the result I've shown previously. You have your insulator in the middle, and you have the superconductors on both sides. But then when you make the metal a little, even more thin, so if it then goes to an even thinner metal, even thinner distance of about less than 10 nanometers, the result looks completely different. So what has happened is the insulator has disappeared, as we had predicted. So that made us very happy. But what is actually very surprising is that the superconductivity is still there. And that actually, we still don't really understand why that's happening. So maybe if there's a very motivated PhD student in the room, they could maybe solve this problem. So anyway, so this takes me to the last part of my talk, which is about moving Moiré patterns. So far, the Moiré pattern was static, and the electrons kind of moved around inside of it. But now we're interested in what happens when the Moiré pattern starts to move. And so here, one simple way we can move it is by sliding the top layer over the bottom layer. And there are three important observations that I want to make about this system. So the first one is that, when you look at the atoms here, you see that the atoms only move a tiny bit, right, relative to one another. However, when you look at the Moiré regions, they actually move a lot. So, and this is a phenomenon that's known as Moiré amplification. The second observation is that this sliding actually requires almost no energy. And this is because in some regions, as you slide, the atoms move from a low energy AB stacking to a high energy AA stacking, so that costs energy. But in other regions, the opposite happens, and so you gain energy, and so the net energy requirement to slide is almost zero. And this is something called superlubricity. The last observation is about the electrons in the twisted bilayer graphene. So we know that the electrons actually follow the Moiré pattern, so they prefer the AA regions. And this is a phenomenon that we call Moiré surfing. So much like a surfer that is transported along by an ocean wave, the electrons are transported along with the moving Moiré pattern. So these are three observations, and they would turn out to be quite useful in explaining our work on another type of Moiré material, which is not based on graphene, but on the transition metal dichalcogenides. So here is an example of the transition metal dichalcogenides. There's a whole class of them, for example, tungsten disulfide or tungsten diselenide. When you look at them from the top, they form hexagons like graphene, but when you look at them from the side, actually the atoms don't sit in a single layer, but you have the tungsten atoms in the middle and the sulfur and the selenium on the top of the bottom. Now again, you can take two of these transition metal dichalcogenides, for example, a tungsten diselenide and a tungsten disulfide, and you can superimpose them. You can put them on top of one another, and what would you expect? You get a Moiré pattern. And this is quite interesting because here you get the Moiré pattern without having to rotate one of the layers. And the reason why you get it is because the sulfur and the selenium atom have slightly different sizes. So the little hexagons have a different area. So when you superimpose them, you get the Moiré pattern. In contrast to graphene, these materials, the transition metal dichalcogenides, actually do not conduct electricity. They're semiconductors. Semiconductors, as you probably all know, are very important. It's what we use to make computer chips. It's also what we use to make solar cells. So it's an interesting question to ask what happens when we have a Moiré semiconductor and we shine a light on them. Well, what happens is that the light gets absorbed sometimes, and this absorption happens through the creation of a bound electron-hole pair, which we call an exciton. These excitons also prefer to localize in certain regions of the Moiré pattern, and it turns out, in this case, they prefer the AB stacking regions. Once they're created, these excitons can also move around, and what they can do is they can hop from one AB region to another AB region, but in order to do that, they have to cross an unfavorable stacking region, and that costs some energy. So this is similar to sort of if you're a hiker and you're in one valley, want to get to the other valley, costs some energy to get over the mountain, right? So where does that energy come from? Well, there's always a little bit of thermal energy available in the material because the material is always at a finite temperature. And if it's that thermal energy that allows the exciton to hop over the mountain, then you would expect that exciton hopping should depend very sensitively on temperature. This is indeed the case. So here, I'm showing you some experimental results from my collaborators at Lawrence Berkeley Lab. So this is led by Antonio Rossi. was working with Archana Raja and Alex Weber-Bargioni. And here you see the exciton diffusion or the exciton hopping as a function of temperature. You see at high temperatures, they hop a lot, and then it goes down quite a bit as you reduce the temperature. But what is interesting, it actually doesn't go to zero. It sort of evens out. And in other words, the excitons still hop around at quite low temperatures. And that was very surprising. So this is something we wanted to understand. And this is the work of Indrajit Mehti, who was a postdoc in my group. And also he worked with Arash. And to understand what's happening, we have to, again, think about the three things we learned about the moving Moiré patterns. The one thing was superlubricity. It requires basically very little energy for the two layers to slide, so they can do that even at very low temperatures. The second bit was Moiré amplification. Even if these layers only move a little bit, if the atoms only move a little bit, the Moiré amplification means that the AB regions move a lot. And then the third bit was the Moiré surfing. The excitons actually move along with the AB regions. So if we take these three things together, what it means is that the excitons can actually move at a very significant speed without ever having to hop over the mountain. And to convince ourselves that this hypothesis is actually true, we carried out a simulation, a computer simulation of the Moiré semiconductor at a finite temperature, and you can sort of see the exciton move around. All right, with that, I'm at the end of my talk. The sort of simplest takeaway message from my talk is, if you put things on top of other things, interesting things can happen. In particular, when we put these two-dimensional materials on top of one another, you can get these very beautiful Moiré materials. They're very interesting properties, and these properties can actually be quite useful. There's quite a few ideas for new devices that are based on these unconventional properties. All right, with that, let me go to my very last slide. So it is said that to raise a child, it takes a village. And as a parent, I subscribe to that view. But it also takes a village to become a professor. And so I've been very fortunate to been able to work with a very big group of very talented and bright PhD students. I've had some excellent postdocs. There have been a lot of important contributions from many master students who were part of the group. Very fortunate to have a great set of collaborators all around the world. And every day I have the privilege to work with my wonderful colleagues, both academic and non-academic, at Imperial College. Finally, let me thank the institutions who provided the money, the funding to do research. The Royal Society generously supported my research with a University Research Fellowship, and we also got some money from the Engineering and Physical Sciences Research Council. Thank you.
Thank you so much, Johannes, for a fantastic lecture. You promised magic. We had magic. We also had exercise, surfing, and lots of science. So thank you so much. You've kindly let us some time for questions. So if there are questions from the audience, we have a bit of time, please. Anyone would like to take the plunge? Yes, please. Go ahead.
Do you think the material is exhibiting changes in their properties due to these Moiré patterns will exist in materials that aren't two-dimensional materials?
Yes, there's many materials. Well, if you have sort of if you create an interface between two bulk material, that interface can also have a Moiré structure. Another example is when you put adsorbates on any surface, there can be Moiré effects. So they're certainly not limited to two-dimensional materials.
Just putting things on top of other things, that's basically. Right. That's what you need. Okay, right. Yes, please.
I suspect the answer might be too technical for me, but curious as to how you know. I'm curious as to how you know that you've got just 2 layers and an angle of 1.1 degrees. Like that seems very hard to.
Yeah, I mean, it did take a very long time to. I showed you the theoretical prediction of the magic angle was in 2011, and the first experimental realization was in 2018, and that was because it's not at all easy to make this. I do have a backup slide, if I can. So there's this method that's called the tear and stack method that people came up with, and it's also very simple. And it basically means you have a graphene sheet, a single sheet, and then what you do is you basically rip that sheet apart. It didn't work very well, but so at that point if you manage to rip the sheet apart, you have 2 perfectly aligned sheets. And now if you have these 2 perfectly aligned sheets, it's much easier to kind of tune into a desired rotation angle. So this is how the tear and stack method works. And that was sort of the breakthrough that then allowed these observations.
Thank you.
Thank you. Yep, one more question. Let's wait for the mic. Please.
Have you looked at any topological effects?
There are there are lots of topological effects. There's the whole community of topological researchers very excited about topological effects in graphene, and in fact, the band structure of twisted bilayer graphene, the bands have topological properties. So there are lots of topological effects in these materials.
Okay, thank you. We have a question at the back. If the electrons could pick up the mic. Sorry. Fine.
So in all your simulations, you've considered a very pristine graphene sheet. Have you sort of considered if there are any natural sort of defects or replacing, say, a carbon atom with another dopant or anything, how that would change the Moiré electronic structures?
That's a very interesting question. Yeah, so obviously sort of the modeling is always an idealization of the real world, right? And then the question is how idealized a version of reality can you get away with? One of the nice things about graphene is that it is remarkably defect-free compared to other materials. So that's why it's a very clean system. But yes, there will be defects, and there will be sort of strain, and the material interacts with the substrate. And yes, we've tried to include some of these effects. We've tried to include what a defect does or what a substrate does. And yeah, they can be quite important.
I had a question actually. When you had your brick and then 2 bricks and then a building. So thinking about sort of carrying on these, we're just talking about 2 layers, but how about further building up?
Yes. So we don't have to stop at the bilayer, and we have been working on tri-layers and quad layers, and there's more new effects when you keep stacking them, and you can twist all 3 of them, or you can twist only one of them, one of the 3. So there's a lot of complicated games you can play, and people do play these games. Okay. So yeah, for sure.
Okay, so you're expecting some more magic properties coming up that we're hearing here first, or?
Yeah. I mean, we are still working on those.
Okay. Thank you. Yes, one more question here. Thank you.
You've been talking about the electrical properties all the time. I was wondering what happens when you shine photons through. Do you get very strange diffraction effects as the light or the radiation goes through the layers, and could that be useful?
It's interesting. I mean, we actually work with people who try to understand the atomic structure through diffraction. So there's definitely interesting. It's quite complicated to disentangle the diffraction spectrum because there's so many things going on. In terms of applications, I'm not sure, but I mean, as a sort of characterization technique, the diffraction is definitely a very powerful one.
a nice link to Thomas Young, maybe. Anyway.
That's right.
Any further? Oh yeah, we've got 2 questions. Yes, Max, please. And then one at the back.
Thank you for a lovely talk. Do you have any best guesses on where the superconductivity comes from in these materials?
It's tricky. It's tricky. The thing with superconductivity, there are always 2 camps. One camp says, it's phonon effect, and the other camp says it's electrons, and both of these camps are absolutely convinced of their viewpoints. So it's kind of hard to be certain. So at this point, I don't have a very strong opinion about where the superconductivity comes from, but well, yeah. I think I'm also just trying to keep an open mind so that if I work on that topic in the future, I don't get too biased myself.
Okay, we've got one more at the back and then one last one. Yes, sorry, I think what at the back and then thank you.
Could you explain the concept of excitons?
Yes. So, well, the first thing is people argue about should it be called an exciton or an exciton. I'm firmly in the exciton camp, but what happens is, that when a photon is absorbed by a material, the energy of that photon can be used to transfer an electron from an occupied orbital to an unoccupied orbital. And so you absorb photon and you create an electron-hole pair. Now the electron carries a negative charge, and the hole, being a missing electron, carries a positive charge. And that means they attract. And much like, an electron and a proton form a bound state that we call a hydrogen atom, the electron and the hole in the material can form a bound state that we call an exciton.
Thank you. And one final question.
Is any work being done on sort of practical applications for what you're discovering?
Oh, yeah. Thanks. That takes me to my other backup slide. So there's a number of things that people think they could be used for. I mean, the key problem is that making these things is quite hard. So, but if you could make them more routinely, then maybe you could think about applications. So, for example, twisted bilayer graphene has a very small band gap, just a few millielectron volts. So that would be a good detector of terahertz radiation, which is something that's quite difficult to find. When the excitons recombine, they emit photons. So these materials could also act as a potential single photon source for emerging quantum technologies. The excitons are very long-lived, so you can actually make lasers out of these materials. And then finally, sort of the thing that I try to motivate it with is people think they can use them as quantum simulators. In other words, as proxy systems to understand the behavior of electrons in materials that are very difficult to study. So, and hopefully, we understand superconductivity. At some point, we can make a room temperature superconductor, and then, we're in pretty good shape. So, yeah, maybe.
Okay, I think we're going to have to bring the questions to a close. Thank you very much again for talk and also engaging in all the questions. And we can give you a clap for this as well. Thank you. So that now brings the last part of the evening. Oh yeah, someone else is controlling the slide. And I'm delighted to welcome Professor Arash Mostofi for the vote of thanks, please.
Thank you. Well, let me first say that it's a real honor and a privilege to have been asked by Johannes to give the vote of thanks for his inaugural lecture, for becoming a professor. So congratulations to you, Johannes. It's also great to see your family here. So your wife, Anna, and your mum, and your father-in-law, Tito. Very, very nice to see you all here. I've got to know Johannes' family a little bit over the years. We have children that are roughly the same age, and so we see them now and again. I've actually known Johannes since he first visited Imperial in 2013. When he was preparing for his application for the Royal Society University Research Fellowship. And that's a position that, as we now know, he won, and he came in 2014 to Imperial. And at that time, I was one of the directors of the Thomas Young Centre, this London Centre for Theory and Simulation of Materials. And I was really excited that Johannes was coming and that we'd managed to attract him to London to host his fellowship for 3 reasons mainly. One was because he had experience of 2 US research groups that I admired greatly. So the group of Thomas Arias, who he showed, and also the group of Steve Louis in Berkeley. These are really great people, and I have humongous admiration for them. So he was coming with that experience. Secondly, because he was bringing expertise in an area that I really thought we needed in London, and that was electronic excitations. And so he was bringing that to us, and I could really see that being useful. And thirdly, because it was really clear to me, even after a short meeting with him, that he was going to be a fantastic colleague and fantastic at science, and he was going to make a huge impact here in London. And so I was really, really delighted that he was going to come. And indeed, it wasn't long before we started collaborating, both in research. So we had a joint project looking at adsorbates on graphene and these weird exotic collapse states. We were teaching together in the Center for Doctoral Training. We had a module together called the Group Research Strategy Project, which was great fun to run. And also in what I call just making stuff happen. Other people call it administration and management, but like just making things happen. And he's great at that. He's great at collaborating to make things happen, because he's just got such a positive and sunny attitude to everything. He's sort of, you know, you can't get him down, basically. Or at least that's how it seems. It's brilliant. So today we've seen a lot about Moiré materials and the magic of Moiré materials. And as you've also seen, this is a relatively new field. The seminal paper was published in 2018. And I actually went back through my emails to see how I got roped into all of this in the first place by Johannes. And so the paper came out in Nature on the 5th of March, 2018. I have an email from Johannes on the 13th of March, 2018 that says, "I have a very time-sensitive research opportunity that I would like to discuss with you. Intrigued? Question mark." So, you know, that was amazing. And well, the rest of that story, you've sort of seen part of it in the inaugural. But what you perhaps haven't realized is that Johannes doesn't just work on Moiré materials. He has huge areas of interest in other things. So he works on how nanoparticles absorb light to create hot carriers. So these are really useful for solar cell applications. And he's developed new methods for predicting the core electron spectroscopy of materials. So this is a really important area for characterizing materials. And he's making huge contributions in those areas too. And for me, really 3 things stand out in my mind about Johannes. One is he's deeply dedicated to his research group and to his research. He supports his research students and research postdocs incredibly well. I've seen that firsthand. He's not limited by what current state-of-the-art methods can do. So if he wants to do something, he has the courage and ability and talent to go and write some new code to do it, right? And very few people are able to do that. And he's an excellent listener, and as you've seen, an excellent communicator, which means that he's able to sustain these really successful collaborations with other theorists, with other experimentalists, and also explain his research to the broader community. So looking forward to the future, these are qualities that I think are going to fuel Johannes' success as a professor going forward. And I think we're going to be very proud. We're going to continue to be very proud of his achievements as the years go by. So Johannes, congratulations.
Right, and I think this, so thank you and congratulations. And I think there are no formal ends to this except to maybe say that there are drinks in the foyer, so where we can all celebrate and continue questioning you on Moiré materials or just letting you relax a little bit and enjoy the moment. So congratulations again and see you all over there. Thank you. Thank you.